We have been talking about P-space, the space complexity class. It is the class of all problems that can be solved in polynomial space. And then we have tried to develop what we call the theory of P-space completeness. The theory of P-space completeness once again allows us to identify hard problems. These are problems that are so hard that if you solve any one of them in polynomial time, then any problem that can be solved in polynomial space would also be solvable in polynomial time. And that gives us evidence that these problems are extremely difficult to solve. We've also seen that the class P-space contains the class NP, and of course NP contains the class P. It's widely believed that P-space is a much larger class of problems than the class NP. Of course, we realize that any problem that is P-space complete must also be NP hard. And so, once we establish that a problem is P-space complete, it's even unlikelier for that problem to be in P than an NP complete problem. So these are problems which are much more general than NP complete problems. They capture a larger complexity class. Of course, the theory of NP completeness revolved around one central theorem, which was the Cook-Levin theorem. The Cook-Levin theorem told us that SAT was NP complete. And similarly, we proved that TQBF, that is, the problem of identifying those quantified Boolean formulas which are true, is P-space complete. TQBF can be thought of as a generalization of SAT. You can think of SAT as a quantified Boolean formula is given to you where all the quantifiers are existential. Similarly, TQBF is a more general class of problems where you're given an arbitrary quantified Boolean formula where both quantifiers are allowed. There exists in for all. And now you're trying to find out whether this quantified Boolean formula is true or not. Once we establish that TQBF is P-space complete, we get our first problem in the class of P-space complete problems. After that, our task of proving other problems to be P-space complete becomes much simpler, because now we do not have to show that every problem in P-space is reducible to our problem that we want to prove is P-space complete, but we only show that TQBF is reducible to our problem. And that shows that all problems are reducible because polynomial time reducibility is a transitive relation. Once we identified one problem which was P-space complete, that gives us a feeling about what kind of problems do we expect to see in the class P-space complete. As we saw, NP-complete problems seem to have an existential quantifier associated with them. So for example, does there exist a clique of a given size? Does there exist a coloring with which we can color the graph using 3 colors? Does there exist a satisfying assignment? These were NP-complete problems. P-space complete problems seem to use both quantifications. And so combinatorial games, a lot of the problems that arrive in combinatorial games are very nice candidates to be P-space complete. Because if you think about a board game, if you want to win the board game, what you want to do is you want to make a move such that for all the opponent's moves, you can make a move such that for all the opponent's moves and so on, that in the end you win the game. So combinatorial games turns out to be a rich class where we can look for P-space complete problems. That was our goal. And so what we did was we proved that a game, a 2-player perfect information game that we call formula game was P-space complete. And the formula game was nothing but a reformulation of QBF. You're given a quantified Boolean formulas, and now 2 players play the game. The first player chooses the existentially quantified variables, and the second player chooses the universally quantified variables. And the goal of the game for the first player is to, in the end, come up with an assignment such that the formula that is the quantifier free part of the formula in question becomes true. And the second player is trying to avoid that. He's trying to make the quantified free part of the formula false. So a QBF can be thought of as a game between two players where there's the existential player and there's the universal player. And since we realized that formula game was just a reformulation of TQBF, therefore it was also P-space complete. However, I have never seen anyone play this game, formula game. I've never seen in real life people playing the formula game because it's an extremely artificial game which maybe logicians would like to play or computer scientists would like to play, but I have never seen anyone play this game in real life. What we want to do is now pick up games which are from real life and show that they are P-space complete. Of course, real life games are a bit vague. All the rules are not completely explained and so on and so forth. So for example, if you've played a game like Scrabble, then, well, unless you have a Scrabble dictionary, what constitutes of a proper English word is debatable, and usually it is context sensitive. Sensitive from, if you play the game in Australia or in England, people will say that different words are allowed in Scrabble or not. So in order for us to precisely come up with games, we must define them mathematically. And so what we started doing was looking at a game called Generalized Geography. And this game was inspired by a game that people play at home and in parties and in gatherings. And this game, we took this game and modeled it using graph theory. And what we would do is prove today that the abstraction of this game that we call Generalized Geography is P-space complete. So today's lecture is going to be exclusively on the proof that Generalized Geography is P-space complete. Let's begin. Let's start by looking at what the game Geography is. Let's just quickly review. We know what the game is, but let's quickly review what the game is, and then we'll look at the abstraction and then go on to prove that it's P-space complete. Let's recall the game Geography. There are two players or two teams in the game, and the first player starts the game and says the name of a city or a town or a geographical region. Player 2 does the same thing. The rule is that player 2 must say a name which starts with the one that the previous name ended with. Then player 1 does the same thing. Once again, one must say a name which starts with the one that the previous name ended with, and so on. In this game, repeats are not allowed, and the first player who gets stuck or cannot come up with a name will lose the game. So the goal of the game is to somehow force the other team to get stuck. So you want to keep coming up with names and hope that your opponent would run out of names and therefore lose the game. Now what we want to do is we want to generalize this game or come up with a mathematically precise definition of a game which models this game. Now what we will do is think of all the names of geographical regions to be nodes in a graph, and then we'll put edges between the vertices. Two vertices A and B will be connected if and only if the last letter of A is the same as the first letter of B. So a part of the graph would look like the one that is shown to you on the screen. So here is a graph in which we have labeled the vertices with different names, and as you can see, two vertices are connected if and only if the last letter of the first vertex matches the first letter of the second vertex. Then we put an edge. So this way what we can do is we can model this game which we call Generalized Geography now. Well, now Generalized Geography is a generalization of geography. And as you see, what is really important is not the names of these places, not the names of the vertices, but the connectivity structure. So the underlying graph is what is important. Notice that when we are studying combinatorial games or two-player perfect information games, we are looking at infinitely intelligent opponents. We are asking the question, what would happen if two infinitely intelligent opponents were to play this game? So if you had people who remembered all the names of all the geographical regions on this earth, and they were able to analyze this graph in their minds, then the real thing about the game will be the underlying structure of the graph. And the underlying structure of the graph will dictate who will win the game, whether the first player or the second player. And so this graph theoretic game becomes an abstraction or a generalization of the popular game that we call geography. So in general, generalized geography would be placed on a directed graph. And of course, what we would do is, to avoid trivialities, we will start with a designated vertex in the graph. So let's think of generalized geography. This game is played on a graph, and it starts with a designated vertex, and player 1 chooses a vertex which is the neighbor of the given vertex. The players continue to select the neighbors of the current vertex, and repeats are not allowed until one of them fails, and that player who fails to find a new vertex loses the game. So you will be given a graph, and there will be a designated start node. The first player will select a neighbor of that vertex, and the second player will select a neighbor of the current vertex. And now the new selected vertex becomes the current vertex, and the next player selects a neighbor of that vertex, and the game continues until one of the players cannot choose a new vertex. In this game, repeats are not allowed. The reason for not allowing repeats is because we want this game to be a finite perfect information game. If we were to allow repeats, then you can ask yourself what will happen if the graph consisted of a cycle. Well, both players will keep alternatingly choosing vertices on the cycle, and the game will never end. However, if we make sure that we put a rule which says no repeated vertices are allowed, then the game becomes a finite game. And the number of moves that will be made in this finite game cannot exceed the number of vertices. In fact, in every move, one of the vertex has to be discarded, and it cannot be repeated. So that shows that this would be a finite game. And between two intelligent adversaries, one player must win. Now, to avoid trivialities, we will require player 1 to start with a designated node. Or what we would do, we would say that the game starts and player 1 has to choose a neighbor of a designated node. The reason for doing this, and notice that this is not a restriction on the original geography game. Well, one of the reasons for doing this is, suppose you have a graph in which you have a node which has no outgoing edges coming from it. Then player 1 will immediately choose that vertex, and the game will end immediately. And somehow the whole structure of the graph would not be explored. Therefore, what we do is we usually designate a vertex, and then player 1 has to start their move. That makes the game generalized geography much more interesting. Now let's formally define the language GG, which we'll call GG or generalized geography, and see what it is. The game GG is the set of all encodings of the pair G, B, where player 1 will win on G when the game is started with B. So the computational question again is, given a directed graph G and a designated node, who will win this game? So if you want to solve this problem computationally, what you will have to do is to write a program which will take as input a directed graph and a designated node to it, or in the graph. And this program will decide whether the first player will win this game or whether the second player will win this game. Let's see how the winning strategy of player 1 would be like. Player 1 has to choose a vertex such that for all choices of player 2, he can choose a vertex such that for all choices of player 2, he can choose a vertex, and you continue this, and in the end what you want is that player 1 wins, or which is equivalent to saying that player 2 gets stuck. So you see, if you think about how a winning strategy would be, it seems to have this alternate quantification in it. There exists a choice for player 1 such that for all choices of player 2, there exists a choice for player 1, and so on. Now, let's say that this game had only 3 moves. And what we want to do is, let's look at a slightly restricted version of it to see this quantification come out. Let's say now we're going to play generalized geography and there are going to be only 3 moves. And after 3 moves, if player 1 doesn't win, he's declared the loser. In this case, player 1 would want to choose a vertex such that for all choices of player 2, there exists a choice for player 1 such that for all choices of player 2, the vertices are repeating. Or in other words, the player 1 wants to choose a vertex, there exists a vertex so that for all choices of player 2, there is a winning choice for player 1. So you can see the interplay of the alternating quantifiers that is happening in this game, or that is eminent or apparent in finding a winning strategy for player 1. Now, this particular feature, whenever you see a problem for which when you try to devise an algorithm, you realize that you are dealing with alternate quantifiers, well, your p-space completeness detector should immediately turn on, and you should of course try to find an algorithm to solve this problem, but you should also start thinking in the back of your mind that maybe this problem is p-space complete. So whenever you had problems in which does there exist some structure, you could suspect that the problem was NP-complete. Similarly, whenever you see alternate quantification happening in your problem, somehow arising naturally in your problem, then you should start suspecting that the problem is p-space complete. So as we see, this question once again seems to be just like an alternating quantified Boolean formula. But the question is it as general as an alternating quantified Boolean formula is? Remember that the alternating quantified Boolean formulas are so powerful that they capture the whole class p-space. And the question is generalized geography general enough game that it can capture all of p-space? Well, for that, all we have to do is just show that it somehow captures quantified Boolean formulas. What we want to do is today prove 2 theorems. The first theorem is going to be that GG is in p-space. And the second theorem is going to be that GG is p-space hard. And once we establish these theorems, we will show that generalized geography is p-space complete. And that's what the definition of a p-space complete problem is. Now, the first thing is, how are you going to show that generalized geography is p-space complete? For that, what I'm going to do is very informally describe to you an algorithm. And the only thing we'll have to check about this algorithm is that this algorithm runs in polynomial space. And that's going to be rather trivial to analyze. But let's look at the following observation, which is very important for us. And once we observe this fact and understand it, we realize that we can use this observation to base an algorithm on it. Let's look at it. So we have this simple theorem which says that suppose G is a graph and player 1 chooses the node B in the graph. So we're looking at a situation where we're looking at a generalized geography being played on a graph, and we're in the middle of the game, and player 1 has chosen a vertex B already in this graph. Now let G prime be the graph with B deleted from G. So we obtain a new graph by deleting B from G, and we let B1 up to Bk be the neighbors of B. So this vertex B that player 1 has already chosen has k neighbors. B1, B2, B3, all the way up to Bk. And we make a new graph by deleting this vertex from our original graph. Now, our claim is that player 1 wins with this move if player 2 does not have a winning strategy by choosing Bi as a move for G prime for all I. So, player 1 has chosen the vertex B. Now, the only choices player 2 has is to either select B1 all the way up to Bk in the graph. And since player 1 has chosen B, player 2 has only the option of selecting B1 or B2 or B3 or B4 up to Bk. And player 2 is now free to choose any one of these vertices. Now, if player 2 does not have a choice from these such that he can win the game, then this must be a winning move for player 1. So this means if we think about it from the current player's point of view, if the current player has played the move B, then it is a winning move if and only if for all I, if the current player plays Bi, that is not a winning move. So this observation tells us that we can come up with a simple recursive algorithm in order for us to find out if player 1 moves G with the current move B. What we do is we recursively find out for G prime and the move Bi for all I, whether that is a player 1 win situation or not. And if all those are not a player 1 situation, then this move B would be a player 1 win move. And of course, once we have this algorithm, once we have this recursion, we realize that in every step of the recursion, what happens is the number of vertices reduces by 1. So the depth of the recursion is going to be at most n. And you realize that on the stack, you will only have to store polynomial amount of information. Therefore, a recursive algorithm based on this idea would have the depth of the recursion would be linear in n, and at any given point, there will be a polynomial amount of information that would be stored on the stack. Well, when will this problem be trivial, or what will be the terminating condition? Well, when the number of nodes in the graph reaches 1 or 0, it's trivial to find out whether the current player wins or not. Therefore, the terminating case of this is also very easy, and we can use this idea to come up with a very simple recursive algorithm. This recursive algorithm takes polynomial space. Now, if you try to calculate how much time does it take, you would realize that it is not a polynomial, it's exponential. It's going to be very long before the algorithm returns an answer. However, what we are trying to do is just to show that this problem can be solved in polynomial space. And when we analyze the space complexity of this algorithm, it turns out that it is polynomial. So, since the algorithm based on this idea requires polynomial space, although it would not be a polynomial time algorithm, this does show us that generalized geography is in p-space. And it was actually a good sign that our algorithm was not a polynomial time algorithm, it was only a polynomial space algorithm. And the reason is that no one actually believes that p-space complete problems do admit polynomial time algorithm. People believe that this is not the case, and therefore it would be highly unlikely if someone can find a polynomial time algorithm for a p-space complete problem. In fact, it would be a big revolution in computer science, a shocking result if somebody were to show for a p-space complete problem that it admits a polynomial time algorithm. That's highly unlikely. Next thing that we want to show now is to show that formula game is polynomial time reducible to generalized geography. Now, since we know that formula game is p-space complete, therefore this would also show us that generalized geography is p-space complete. So, once again, this is where our previous result, which showed that TQBF was P-space complete comes into play. We know all problems in P-space are polynomial time reducible to TQBF. We know TQBF is polynomial time reducible to formula game. And now if we establish that formula game is polynomial time reducible to generalized geography, then transitivity shows us that all problems in polynomial space are reducible to generalized geography, and therefore generalized geography is P-space complete. How would we do this? Well, what we would do is we will show that if you're given a quantified Boolean formula phi, what we can do is we can make a graph G sub phi such that phi is true if and only if player 1 wins on G sub phi. So remember the input to a quantified TQBF or input to a quantified Boolean formula problem. The input looks like a quantified Boolean formula, and the question is whether this quantified Boolean formula is true or not. By looking at this formula, we will create a game, and this game will have the property that player 1 will win this game or will have a winning strategy for this game if and only if the original formula happened to be true. If the original formula was false, then player 2 will have a winning strategy. Thus, the question of whether a quantified Boolean formula phi is true or not can be converted into the question of who wins this generalized geography game. Notice that this reducibility, G sub phi, must be computable from phi in polynomial time. We cannot take too much time in order to compute G sub phi. We must be able to do it in polynomial time. Once I describe to you G sub phi, you'd see that it's almost trivial to see how to compute G sub phi from phi. The trick is in defining G sub phi. The structure of G sub phi has to somehow relate to the structure of phi. Phi is a Boolean formula. G sub phi is going to be a graph. Well, so let's take a formula phi, and this formula is a quantified Boolean formula, and therefore phi is equal to there exists x1 for all x2, there exists x3 all the way up to some quantified with the kth variable, and then psi. And here we will assume, for the case of simplicity, that the quantifiers alternate. The quantifiers alternate meaning the first quantifier is the existential one, then there's a universal quantifier, then there's existential quantifier, then there's a universal quantifier, and so on. And the second assumption that we'll make is that psi is in CNF. So, the first assumption is not a major or a complicated assumption. What you can do is you can convert any formula, quantified Boolean formula, into one that has quantifiers alternating by adding dummy variables and quantifying them and inserting them in the formula. The other assumption that psi is in conjunctive normal form, that's a slightly more complicated assumption. However, QBF is known to be P-space complete even when psi is restricted to be in CNF, and that will actually comes from the proof of TQBF. If you examine that carefully, you realize that the eventual formula that we output could have been outputted in conjunctive normal form. So we have these two assumptions. We are given a formula phi with alternating quantifiers, and then it has a quantifier free part psi, and psi is in conjunctive normal form. Now the graph G sub phi, which I have to describe to you, is going to be described in two parts. The first part is going to have n-diamond structures, one for each variable, and the start node is going to be B. So let us look at this part of the graph. In this picture you see n-diamond structures, and each diamond structure has 4 nodes in it, and 2 nodes on the side are labeled by T or F, and each diamond actually corresponds to a variable. Let's say that this diamond structure was the input to generalized geography, and let us say that the start node was already given as the top node, B. then how will player 1 and player 2 play this game? What would that correspond to? Let's analyze this, and that would give us a clue as to how this graph is going to capture our quantified Boolean formula. The game starts at the node B. Player 1 has to choose a neighbor of B, and it has only two neighbors, T1 or F1. Once you're on T1 or F1, there's only one outgoing edge. So player 2's move is forced, and he has to choose Z1. And from there, once again, there is only one outgoing edge. So player 1 has to move is forced, and he can only choose B2. Now it's player 2's turn, and he can choose T2 or F2. Player 1's next move is forced again, and he has to go to Z2. Player 2's next move is forced again, he has to go to B3. And now player 1 can choose T3 or F3. So, if you think about what's happening, player 1 made a choice. He had two choices between T1 and F1. And then next couple of moves were forced. Then player 2 made a choice. And then next couple of moves were forced. Then player 1 made a choice. And then next few moves were forced. And the game proceeds like this. So let's see what exactly is happening. Let's give an interpretation to the choices that the players have made. What we observe is if I is odd, then player 1 chooses Ti or Fi. So player 1 chooses between choosing Ti or Fi. On the other hand, if I is even, then player 2 chooses between Ti or Fi. All other moves are forced. Well, the choices Ti or Fi are the assignment of player 1. Remember, player 1 in the formula game assigns the existentially quantified variables, and player 2 assigns the universally quantified variables. Now, the way we have set up, if psi has alternating quantifiers, then for odd I, player 1 should be assigning values to those variables, and for even I, player 2 should be assigning values to those variables. And by choosing whether to go this way or that way, player 1 and player 2 are assigning true or false respectively to their variables. So, this simple observation has an interpretation. Player 1 is choosing the existentially quantified variables, and player 2 is choosing the universally quantified variables. The game eventually ends at the node C. So, if you think about how the game will be played on this diamond structure, player 1 will be making choices which we can interpret as choosing variables, existentially quantified variables. Player 2 will be making choices which we interpret as him choosing the universally quantified variables. The game continues, and it will eventually end at the bottom node, which we have designated C. The question is, whose turn would be when we reach the node C? Well, that depends on n, the number of variables in this diamond structure, because if the number of variables turns out to be even, then it would be one player's turn, otherwise it would be another player's turn. But we can make sure that it's the first player's turn by adding one extra node before C if needed. So if the parity of n is not correct, then we can correct it by adding one extra node and make sure that it's a designated player's turn when they reach the node C. So this was the first part of the graph. And when the game is played on this graph, the choices made by player 1 and player 2 correspond to an assignment of the variables. The existentially quantified variables were chosen by the first player, and the universally quantified variables were chosen by the second player, and the game ends at a designated node. There are no other possibilities that can happen in this particular game. Now let's look at this designated node C. This vertex in the graph is going to have outgoing edges to C1, C2, Cm, where each Ci is a clause in psi. Notice that the first part that I described to you in this graph can be made without ever looking at the quantified Boolean formula. The only thing that you need to know is how many variables does the quantified Boolean formula have. If it has n variables, then you put n diamonds. So the whole graph doesn't seem to depend on the formula phi. However, the second part does depend on the formula phi. In fact, it's the quantifier free part psi that we are going to look at. So we look at this quantifier free part psi, and that has m clauses. Remember, we said that psi has to be in conjunctive normal form. So it's going to be a bunch of clauses and it together. So if it has m clauses, then the last vertex c will be connected to m vertices, one for each clause, C1, C2, C3, C4, all the way up to C sub m. And then now the interesting part of the graph will come. This is where actually the graph will depend on the formula very, very heavily. In fact, we'll have to look at the formula psi in order to make the rest of the graph. So far, the part that we have made, we only need to know the number of vertices and the number of clauses, number of variables and the number of clauses in our formula. From the clause nodes, there are edges to nodes labeled by literals of the clause. Each clause has its own copy of the literal. So let me explain. Suppose you had a clause C1 and there was x1 or x2 bar or x3. Then C1 will have three edges coming out of it. One will be going to a literal, which will be labeled x1, the other one will be labeled x2 bar, and the third one would be labeled x3. However, now these literal vertices will connect back to the diamonds. Let's see how that is done. From the literal xi, there is going to be an edge to ti. And from the literal xi bar, there is going to be an edge fi. So in other words, what we're doing is we're connecting a literal to the original node if and only if that assignment was going to make this literal true. So for example, x3 bar will be connected to f3. So if the player somehow chose their assignment in such a way that x3 bar happened to be false, then this edge is going to go to f3, a node that is already used. On the other hand, if they somehow chose an assignment in which x3 was true, then from this particular node, there's one possible move left, that is to go to f3, because f3 was not chosen by both players in their assignment. Here is a picture of that I've made for the clause C1 equals x1 or x2 bar or x3. As you can see in this picture, C1 is connected to literals which are labeled x1, x2 bar, and it's also connected to a vertex which is labeled x3. Now x1 is connected to t1, x2 bar is connected to f2, and x3 is connected to t3. So it's very simple to look at this formula psi and start building this part of the graph. All you have to do is just add nodes and edges going back to the diamond structure that we have made before. So here is how the whole graph would look like. As you can see, one part of this graph is the diamond structure, and the second part of this graph corresponds to the quantifier free part psi. And the diamond structure is just a very, very simple structure, and the quantified free part tells us how to make connections from the CIs to the literals which go back to the diamond structure, which is the first part of the graph. So by looking at the formula phi, it should be very easy for you to see how to compute this graph G sub phi. Now our game is complete. This game is going to be G sub phi, it's played on this graph, and the start node is the first node B. So how will this game be played, and who will win this game? Let's try to analyze it. Let's consider the game from player 2's point of view when the current vertex is C. Note that the choices made by the two players dictate an assignment. So if the game starts with the vertex B, which is the beginning, remember that there are no edges which are going from the diamond structure to the rest of the graph other than from the vertex C. So that's like playing this game only on this part of the graph where you completely can ignore the rest of the graph till you reach the vertex C. And we've seen that as the two players play this game on this diamond structures, what they're doing is alternatingly assigning values to their respective variables. So if player 1 chooses T1, he is set x1 equals true. If player 2 chooses f1, he is set the second variable to be false, and so on and so forth. So when we reach the vertex C, let's see from the player 2's point of view, how would he try to win the game? Let's say that the current vertex is C and it's player 2's turn. Then he would like to choose a CI such that he can win from that clause. So he would like to choose a clause such that he can win from that clause. But how is it that this player can win from the clause? Well, player 1 has no other choice from that clause, move to a literal in the clause. And player 2 can only win if that literal is made false by the assignment. So if the literal is made true by the assignment and player 1 moves to that literal, then there is no way for player 2 to continue the game and he loses. So player 1 will want to send him to a literal that is made true by the assignment. So in other words, player 2 would want to move to a clause such that all the literals of that clause are made false by the assignment. Player 2 is trying to move to a clause such that all the literals in that clause are made false by the assignment. And therefore, player 2 is going to move to a clause that is made false by the assignment. So you see, player 2, after the first round of the game has finished and they have reached C, and now player 2 has to go from C to a clause, player 2 would want to move to a clause that is made false by the assignment. This means if there is a clause which is made false by the assignment, he'll win. However, if somehow the assignment that they chose was an assignment which makes all the clauses true, then no matter what clause he moves to, player 1 will choose a literal that is true in that clause, and then he will have no more moves left. This means that when they were choosing the assignment, during that part, player 1 was trying to make the formula true by choosing his variables, and player 2 was trying to make the formula false. Thus, player 2 wins if there is a false clause. Otherwise, player 1 would win. And therefore, in the first part of the game, player 1 would want to reach an assignment which was making the formula true, and player 2 would want to reach the assignment which would make the formula false. So while choosing the assignment, player 1 will try to make psi true and player 2 will try to make psi false. So in other words, these two players are now playing a formula game, or the formula game is being simulated by this generalized geography. What is happening is, instead of player 1 and player 2 making assignments to their variables, they're choosing nodes in the graph. And those nodes in the graph are the choices that are telling them whether the variable was set true or not. The rest of the game also, the outcome of the game depends on what that assignment did to psi. If the assignment made psi true, then player 1 wins, and if the assignment made psi false, then player 2 will win. Now, so if the quantified Boolean formula is true, then we know that player 1 wins the formula game, and therefore G sub phi would be won by player 1. On the other hand, if phi was false, then we know that player 2 wins the formula game, and therefore generalized geography played on G sub phi will be won by player 2. Thus, we have this very nice theorem which says that player 1 wins G sub phi starting with B if and only if psi is true. And this establishes our reducibility. So let's think a moment and see what we were able to do with this game, Generalized Geography. Well, when I think about this reduction, it always reminds me of the reduction that we did when we were reducing satisfiability to Hamiltonian cycles. However, I find this proof much easier and much more natural. What we did was, we said that we have a formula phi which has variables, and we took a particular form of it which was alternating quantifiers, but that was a minor detail. But phi was a formula with quantified variables, and we made a diamond structure which corresponded to the variables in this formula. This diamond structure was made, and it forced players at various places to play the game in a certain way. However, at certain places in this diamond structure, it gave players choices. By tinkering this thing and perfectly aligning it and putting proper number of nodes, we said that all the choices that are made by player 1 will correspond to existential variables, and all the choices that are made by player 2 will correspond to assigning universal variables. And the game had to end at a designated node C. From C, it was player 2's choice. And the rest of the connections were made in such a way that player 2 wanted to reach a false clause, a clause that was false. And if he reached a false clause, then no matter where player 1 sent him, he still had one more move left, and that was the last possible move, because we were going back to the diamond structure. Therefore, what player 2 wanted to do was to move to a false clause. On the other hand, player 1 would succeed if somehow the assignment was such that it made all the clauses true, because then player 2 would not be able to find a false clause and player 1 would win the game. Therefore, we've reduced formula game to generalized geography. Since formula game is p-space complete, therefore we've shown that generalized geography is also p-space complete. So the theorem that we have proved today says that generalized geography is a p-space complete problem. Generalized geography, of course, comes from a class of problems, a large class of problems, and it's a combinatorial game. It's a two-player perfect information game, and this perfect information game happens to be p-space complete. As I told you, there are a lot of other games which turn out to be p-space complete. For example, games like chess, hex, go. There are some other very nice board games, several of whose versions turn out to be p-space complete. Games often are hard to solve. As you can see, that to solve a game, somehow you have to come up with a strategy which automatically lends you to thinking, I should make a move such that for all of my opponent's move, and so on and so forth. So games naturally have some kind of an alternating quantification built in them. And usually this alternating quantification can be used to show that they are p-space complete. Well, one of the ideas for you doing a project is to actually go on to Google and look at p-space complete and combinatorial games and read some of the very nice proofs of p-space completeness of hex and other games, which are very, very interesting. Although the theory of p-space completeness is very interesting, but from a computational point of view, p-space complete problems are very, very difficult to solve, because we suspect that NP-complete problems cannot be solved in polynomial time. Therefore, we also believe that no p-space complete problems can be solved in polynomial time. Now, this means that we are studying an extremely hard class of problems. And from a theoretical point of view, from a point of view that these interesting questions capture complexity classes, that's really wonderful. However, the theory of p-space completeness is so far beyond, the problems which are p-space complete are so far beyond our computational reach that it is not extremely practical. Remember that somehow we think of practicality, those problems that we can solve in practical time, tractable problems, we consider that boundary to be the boundary between P and everything else. So anything that can be solved in polynomial time, not polynomial space, is considered to be solvable in practice. Therefore, p-space completeness is actually the study of very hard problems. In the next lecture, what we will do is we will actually now go down inside P and define two space complexity classes which are within P and start building a theory of completeness over there. That's going to be the next lecture. I'll see you next time. Thank you and goodbye.